welcome to the first video in the core tutorial series of the new YouTube channel, Learn Algorithms. Today's topic is going to be modular arithmetic. The format of these tutorials is going to be such that I will start with a very high-level view of the topic at hand, and then supplement that with a slideshow consisting of examples and some mathematical derivations. Today's topic is modular arithmetic, so let's get started. When you think of the division that you learned in elementary school, division of integers returned two values to you, returned a quotient and a remainder. Traditionally, we were only concerned with the quotient. For example, 7 divided by 2 would yield a quotient of 3 and a remainder of 1. With modular arithmetic, it's a little bit different. We are only concerned in the remainder and do not care at all about the quotient. The mathematical way of describing this is you would say that the remainder returned when 7 divided by 2, or 7 mod 2, is 1. As we are only concerned with the remainders, we can start to talk about new notions of equivalence between numbers. Two integers, call them x and y, are equivalent modulo some third integer n if the remainder that is returned when they are both divided by n is the same. For example, 7 divided by 2 has a quotient of 3, which we don't care about, and a remainder of 1. Similarly, 5 divided by 2 has a quotient of 2, which we again don't care about, but it also has a remainder of 1. Therefore, we would say 7 and 5 are equivalent modulo 2. Modular arithmetic has many uses in computer science. For one, it's used a lot in cryptography, as we'll see in a few videos when we cover RSA cryptography. It also has many uses in everyday life. For example, in the Gregorian calendar, the week resets after every 7 days, so you can think of the days of a week as being modulo 7. Similarly, on a 24-hour clock, we can think of time, at least in hours, as being modulo 24. For example, 7 a.m. would be 7 mod 24, which is a quotient of 0 and a remainder of 7. If we were to talk about, say, 25 o'clock, that would be 25 mod 24, which has a remainder of 1, or 1 a.m. I will now cut to a slideshow to cover some of the more mathematical properties of modular arithmetic, as well as a few more in-depth examples. Okay, let's start with some of the basics of modular arithmetic. Thinking back to grade school when you were learning integer division, anytime you divide some integer x by another non-zero integer y, you get two numbers back. You get a quotient and a remainder. As we talked about, historically, you were really only interested in the quotient, but with modular arithmetic, the quotient is completely irrelevant. You are interested only in the remainder. Note also that the integer y that's dividing x has to be non-zero. Division by 0 is still undefined in modular arithmetic. To give a quick example, say x was 7 and y was 2. 7 divided by 2 gives us a quotient of 3 and a remainder of 1. Again, since we don't care about the quotient, we throw away that value and take the remainder of 1. What this means is that 7 mod 2 is equal to 1. Here again we just see this is shown mathematically as, for some integer x and some integer y, x mod y, which simply returns the remainder when x is divided by y. Since we're talking about remainders, we can now talk about new notions of equivalence amongst integers. As we're completely discarding quotients, we can talk about equivalence specifically in terms of remainders. Two numbers are equivalent modulo some number n if they give the same remainder when we divide them by n. So for example, since 5 mod 2 is 1 and 7 mod 2 is 1, that is, when both of those numbers are divided by 2, they give a remainder of 1, we would say that 5 and 7 are equivalent modulo 2. And then in the formula or equation at the bottom of your screen, the triple bar equal sign stands for logically equivalent. So 5 is logically equivalent to 7 mod 2. An interesting property of modular arithmetic is that if x is equivalent to y mod n, then we can infer that n evenly divides the difference of x and y. Why does this matter? Well, if you have two integers x and y, and you're curious to see if they're equivalent modulo some third integer n, you can very quickly check this by simply taking the difference of x and y and dividing them by n. If you get a remainder of 0, then x and y are equivalent modulo n. If you get a non-zero remainder, then they are not equivalent modulo n. So as a quick example, 7 is equivalent to 5 modulo 2, because 7 minus 5 is 2, and 2 divided by 2 equals 1 with a remainder of 0. Note that it doesn't matter in what order we take the difference. We could have done 5 minus 7, gotten negative 2, negative 2 divided by 2 is negative 1 with a remainder of 0. As long as the remainder is 0, this test works just fine. That just about covers the basics of modular arithmetic. In our next videos, we'll talk about modular multiplication and division, as well as modular exponentiation. After that, we'll talk about some modern applications of modular arithmetic to the RSA cryptography system. Thanks for watching, and again I ask that you please leave comments in the comments section saying what you liked, what you didn't like, and what you'd like to see more of. Thank you.